If you're driving down the highway and you want to see how fast you're going, it's easy. You just look down at your speedometer. If you're in a lab and you want to see how fast a chemical reaction is going, it's a little more complicated. In this video, we'll look at a few factors that influence the speed of chemical reactions. This video is part of the Equilibrium video series. It's often important to determine whether or not a system is at equilibrium. To do this, we must understand how a system's equilibrium state is constrained by its boundary and surroundings. Hi, my name is George Zaidan, and I'm a graduate of the chemistry department right here at MIT. Before watching this video, you should have a basic understanding of chemical equilibrium. After watching this video, you'll be able to understand how reaction rate is influenced by reactant concentration, explain how reaction rates change as a system establishes equilibrium, and predict relative equilibrium concentrations of reactant and product based on rates of forward and reverse processes. Suppose you have this general reaction, where capital letters A, B, C, and D are molecules, and lowercase a, b, c, and d are their molar coefficients. As the reaction progresses, A and B will be consumed, and C and D will be formed. Now, the speed at which any of these four processes happen, multiplied by the reciprocal of the appropriate molar coefficient, is called the rate of this reaction. If you want your car to go faster, you step on the gas. But speeding up a chemical reaction is not that simple. There are lots of different factors that affect reaction rate. Three common ones are the concentration of the reactants, the temperature of the reaction mixture, and the presence of a catalyst. In this video, we'll focus on the effect of concentration on homogeneous reactions. Most chemical reactions are the result of two or more molecules colliding with each other. But not every collision leads to a reaction. The molecules must collide in the proper physical orientation, and they must do so with enough energy to break their bonds. Imagine a beaker with 100 milliliters of water, in which you dissolve 10 to the 6 molecules of reactant A and 10 to the 6 molecules of reactant B. How likely is the reaction to form C and D? Do a back-of-the-envelope calculation to support your answer. Pause the video. So let's see. 100 milliliters of water is 100 grams of water, which is 100 over 18.02, about 5.5 moles of water. That means there are about 3.3 times 10 to the 24 molecules of water in that beaker, and only 10 to the 6 molecules of each reactant. So in any given volume of this solution, 3.3 times 10 to the 24 over 3.3 times 10 to the 24 plus 10 to the 6 plus 10 to the 6, so 99.99999999999999999999999% of molecules are non-reactive water. Clearly, successful collisions between the reactants would be very rare in this situation. Now, intuitively, you would expect that the more concentrated the reactants, the faster the reaction, and this is generally true. Let's draw a reaction coordinate diagram to better understand our hypothetical reaction. The x-axis is the progress of the reaction, and the y-axis is potential energy. Here are the reactants, and here are the products. We'll assume that the reaction is exothermic, in other words, that energy is given off as the reaction progresses. So we draw the curve like this. This hump, this is the activation energy, the point of highest potential energy of the reaction. Two molecules must collide with at least this amount of energy in order to successfully react. Do you notice anything about this diagram? There's no indication of directionality. In other words, there's no reason that the reaction couldn't proceed backwards just as well as forwards. You're probably used to thinking of chemical reactions as processes that happen in only one direction, forward. But most reactions are actually reversible. There are a few exceptions, for example, combustion. You can't unburn a match. But most reactions that chemists carry out in the lab or that happen in our bodies are reversible. Draw your own reaction coordinate diagram and label the forward and reverse reaction paths. Suggest what the relationship might be between the activation energy and the relative rates of the forward and reverse reactions. Pause the video. This is the activation energy for the forward reaction. The higher this activation energy, the slower the forward reaction, because the number of reactant molecules with sufficient energy to react when they collide will decrease. But now let's look at this picture in reverse. The reverse activation energy is not the same as the forward activation energy. In this particular case, it's higher. So that means that the reverse reaction will be slower than the forward reaction. If we were to somehow increase this activation energy, both the forward and the reverse rates would slow down, but the relationship between them, namely that the forward rate is faster than the reverse rate, would be preserved. Here are 4 other diagrams, each for a different hypothetical reaction. Predict the relative rates of the forward and reverse reactions in each of these cases. Pause the video. In this one, the forward activation energy is higher than the reverse activation energy, so the forward rate is slower than the reverse rate. In this one, the forward activation energy is lower than the reverse activation energy, so the forward rate is faster than the reverse rate. In these two, the forward and reverse activation energies are the same, so the forward and reverse rates would be the same. In real-life chemical processes, the rates of the forward and reverse reactions are often very different. Many of the reactions that you may have previously thought of as irreversible actually just have wildly different forward and reverse rates. For example, you've probably seen the dissociation of a strong acid in water written like this. But really, it's this. In this case, the forward reaction is many orders of magnitude faster than the reverse reaction, so we write it as just the forward reaction.